Let's do one example using the kinematic equations for rotational motion. So we have a high-speed drill rotating counterclockwise, takes 2.5 seconds to speed up to 2400 RPM. What is the drill's angular acceleration? So the first thing is to always visualize the problem so you can figure out what type of problem it is. You have something rotating, you're told that it's speeding up and that takes a certain amount of time. So that's a good indication that you're going to use the kinematic equations because you have initial speed, final speed, time, and we're looking for acceleration. But now the difference is that the object is rotating instead of moving in a straight line, so we're going to deal with all angular quantities instead of linear quantities. We're going to work on these problems the same way that we used to with the kinematic equations for linear quantities. We're going to write down our givens. So we have time here, 2.5 seconds. And then that's the time to speed up to a speed of 2400 RPM. So we're going to assume we're starting from rest. So instead of writing v initial, we're going to write omega initial. The initial angular speed is 0. We just care about the angular speed in this, the angular quantities in this problem because we're looking for angular acceleration. And then the final angular speed is going to be 24 RPM. So RPM stands for revolutions per minute. So we do need to convert that to radians per second, which is the SI unit. We learned that 1 revolution is 2 pi radian. We put the revolution on the bottom so that it cancels out. And then we have to get rid of the minutes. We know that in 1 minute there are 60 seconds. So that will cancel out the minutes when the minutes is on top there. So we need to multiply 2400 by 2 pi by 60. And that gives us 251 radians per second, where I'm not rounding in my calculator, just on the screen here. And we're looking for acceleration, angular acceleration. So we have defined 3 variables. We're looking for the 4th one. We need to figure out which equation to use in order to solve for the acceleration. So if I go back to the equations, we see that we have omega initial, omega final, and we have time. We're looking for alpha. So we're going to use this first equation here. It has all the variables that we need. I'm going to write it down. Omega final equals omega initial plus alpha times time. Omega initial, angular velocity initial was 0, cross it out. We're looking for alpha. Alpha is going to be omega final divided by time. We plug in 251 divided by 2.5 seconds, and we're going to get 101 radians per second squared. So that's just to give you an idea of the numbers. An angular acceleration of 101 radians per second squared is typical for a high-speed drill. And now let's do part B, which you might be able to relate a little bit more to. Part B asks, how many revolutions does it make as it reaches top speed? What do you think? In 2.5 seconds, how many times can it spin? So the first thing is that whenever it's a problem says revolutions, what needs to come into your mind is that this is an angle. You know that 1 revolution is 2 pi radians. And 2 pi radians, that's an angle. So just a reminder, whenever it says revolution, you want to go ahead and define delta theta. In this case, delta theta is what we're looking for. Let's write down our givens. We have the time, 2.5 seconds. We have the final angular speed, which we had converted into part A, which was about 251 radians per second. And then we also have the initial angular speed was 0. I always like to use the givens as much as possible to avoid rounding as much as possible. Technically, we just found the angular acceleration, so we have many choices for which equation to use to find the delta theta, but since I'm writing down omega initial, omega final, and time, then this third equation here is the best one to use because it will let us solve for delta theta. Let me go ahead and write it down. That third equation said delta theta equals 1/2 omega initial plus omega final multiplied by time. Now you can use another one with the angular acceleration if you want to. You do have options. You'll get the same answer. Omega initial is 0. We're going to plug in 1/2 times 251 times 2.5, and that's going to give us 314 radians. Common mistake in these problems is students forgetting to really pay attention to the units. So we did find the angle, but we want it in revolutions. So let's go ahead and convert that to revolutions by doing the conversion that 2 pi radians is equal to 1 revolution. So we need to divide our number by 2 pi. And that's going to give us about 50 revolutions. And one more important note here, common mistake when you do this in your calculator, make sure to put 2 pi in parentheses. Otherwise you're going to get a different number because your calculator is going to think that you're dividing by 2 and then multiplying by pi. So in the calculator, put 2 pi in parentheses to make sure that you're dividing by the whole thing. So this was an example of using the kinematic equations. Remember that we're using these equations the same way that we used them when we talked about linear motion. So feel free to go back to one of the first videos that I made going over the kinematic equations with the linear quantities.